So, picking up from where we left this problem off, we determined that this problem was stable and was determinate, and now our goal is to solve for our unknown reactions. So the first thing I look at is the free body diagram that we've already drawn here. And I can see we've got 1, 2, 3, 4, 5 unknown reactions. I have a single free body diagram, so I have too many unknowns. So what I need to do is break this apart. So let's go ahead and break this into 3 free body diagrams, and we'll analyze each one. I'll go ahead and do that down here. So free body diagram number 1 has the unknown reactions, and it has our linearly varying load. But we also, with points A, B, point C is a pin, free to move. So on point C, what I get is 2 reactions. And the 2 reactions I get from the other member, we'll call them CX and CY. And it doesn't really matter how I draw these. If I draw them to the left and upward and I get a negative number for my answer, then I just know that I have drawn them in the wrong direction. The big thing is I need to be consistent. So there's free body diagram number 1. And I look at that and I said, well, I've got 5 unknowns and only 3 equations of equilibrium. So I could go ahead and start writing equations here, but I'm going to start investigating the other free body diagrams as they connect together and see if I can solve one of them a little bit easier. So let's jump to free body diagram number 2. Okay. Now free body diagram number 2 is 6 feet long, and it's what we call a 2-force member. A 2-force member is one that can, if it doesn't have any internal loads, can only have an axial force. But I'm going to go ahead and put the reactions on, and we'll prove that to ourselves in a minute. So if CX is going to the left up here, I'll apply it to this side going the other direction. And CY is going up there, so I should apply it down. And similarly at the bottom, I get dx and I get dy. Okay, so again, I have 3 equations of equilibrium and 4 unknowns here, so I can't solve this one directly. However, I can start setting it up and seeing what kind of relationships I get. So let's go ahead and do that. Let's sum our forces in the x direction, to the right being positive, and I get Cx plus dx. So I don't know what they are, but I do know that Cx has to equal minus dx. That's a nice simple equation that we can use in the future. Let's go ahead and sum our forces in the y direction equals 0, and I get minus cy plus dy has to equal 0, so cy has to equal dy. Okay? So there's another nice simple one. And let's go ahead and sum our moments about point C. I can pick any point. I'm going to pick C, counterclockwise being positive. And you'll note that the moment of Cx, Cy, and dy about point C are all 0 because they have 0 lever arms. But I do get a lever arm for dx. And that lever arm is equal to 6 feet times dx. But that has to equal 0. So if I sum my moments about this point, there's nothing else balancing that dx. Therefore, I can conclude that dx is equal to 0. So I did get one solution out of here, and that's typical. You may have an indeterminate structure, which this free body diagram is indeterminate, but I can still solve partially. Dx being 0 plugs in up here, tells me Cx is equal to 0 as well. Okay, so Cx is equal to 0. So those are really useful to me. I can go ahead and write that in right here. 0 kips, 0 kips, and 0 kips. And I have this relationship here where Cy equals dy, which is going to help me. So let's jump down to our next free body diagram. And I've put in our unknown reactions. I've put in our resultants of our inclined load. And then I'm going to go ahead and put dx here and dy here. Now we know that dx is equal to 0 from up above. So now we have for free body diagram number 3. Okay, 3 unknowns and 3 equations of equilibrium. So we can go ahead and solve this one. So let's go ahead and do it. Let's look at the sum of the forces in the x direction to the right being positive, have to equal 0, equals dx minus 3 kips plus rex. But we know that dx has to equal 0 from up here, so we can conclude from this that rex is 3 kips. Okay. And does that make sense? Sure, it makes a lot of sense. We have a horizontal force of 3, and the vertical member up here from free body diagram 2 really can't provide any resistance. So it makes sense that rex is 3 kips. Next question, we need rey and dy. So let's do a moment equation. Sum of the moments. Let's sum the moments about point D, counterclockwise being positive. And we get 4 kips times 6 feet, and that's going counterclockwise. That's going clockwise, so it's a negative. There's no moment of the 3 kips or rex or any of the loads at D, and the last one would be rey at 8 feet. And that's going positive, so I add those up, and that has to equal 0. So rey has to equal 1/8 times 4 kips times 6 feet. I lost my negative sign by bringing rey over to the other side. That's 24 divided by 8, and I get 3 kips as well, rey. So I've solved for the bottom 2 reactions. They're both 3 kips. Because I got positive numbers, it tells me they're both going in the same direction, as I assumed. The last equation of equilibrium down here is the sum of the forces in the y direction have to equal 0. We'll do up being positive, and we get minus dy minus 4 kips plus rey. So solving that for dy, I get dy equals minus 4 kips plus 3 kips is equal to minus 1 kip equals dy. What this tells me is that because it's a negative sign here, dy is negative, that tells me that it's actually dy is going up. Okay, 1 kip. So I had made a bad assumption, but I caught it in the negative. So now we can back substitute through our other equations. If we jump up here, let me zoom out a little bit, and we can do some back substitution. We can take this and plug it in here, and we get cy equals dy equals minus 1 kip. Again, let's keep that negative in there, or so we can track it through. And this brings us back to our first free body diagram. Now cy is equal to, we just said minus 1 kip, which is the same as saying it's 1 kip going down. Okay. Now we only have 3 unknowns in free body diagram number 1, and we can solve them. So let's go ahead and solve the easy one first. Zoom out a little bit here. Sum of the forces in the x direction equals 0, to the right being positive, equals rax minus cx. Again, we can see cx is equal to 0, so we can conclude right here that rax is equal to 0. Makes sense. No horizontal loads applied, so no horizontal reaction. I'm going to sum my moments about point A equal to 0, counterclockwise being positive. The forces at RA drop out because they go through that point. CX is 0. So let's just go left to right. I get 8 kips per foot times 9 feet over 2. That's the area of my triangle. So the resultant is equal to 8 kips per foot times 9 feet, which is the whole to bottom, divided by 2. And it acts at the 1/3 point. So the 1/3 point would be 6 3. So that acts at 6 feet from point A. and it's going in a negative sense. Okay, it's going this way, so I have to have a negative on there. I get RB y times 6 feet, and then I get our CY. CY, so this one here is going this way, and the last component I get is CY times 9 feet. Okay, the way I've got it drawn, CY is going this way, but when I put the negative in front, -1 in there, -1 kips, it's really important to watch that sign. I end up with 0 equals -8 times 9 times 6 over 2, that's kips per foot, that's feet, and that's feet, plus, that's a negative, plus 6 RBY minus 1 kip times 9 feet. Okay, so that was a plus the way we were drawing it, but the negative comes from the -1, and I can solve this for RBY. So in this case, RBY is going to equal 1/6. Bring it over to the other side. The other two get positive signs. That's 72 kips times 6 feet over 2 plus 9 kip feet. And I get RBY is equal to, what do I get? 37.5 kips. Okay. And then the last equation I need to solve for is for RAY. So I'm going to jump up here. Sum of the forces in the y direction have to equal 0. Up being positive. RAY minus, here's this up here is 36 kips, minus 36 kips, and then minus 1 kip, and plus 37.5 kips, and I get RAY is equal to 0.5 kips going up. And I have solved for all my reactions. So if we zoom back out and walk through it again, the steps we took were, first, look at our structure and draw a free body diagram. So we drew the free body diagram here. We couldn't solve for all our unknowns here. We had 5 unknowns and only 3 equations of equilibrium. We want to see if we can actually solve this problem. So we check stability. Our reactions are not all parallel, and they don't all converge at one point. So we've checked this odd case of stability. Then we jumped over here and we checked determinacy. We had 9 unknowns. We had 3 members times 3, 9 equations of equilibrium. So we concluded it was determinate. And then we started to break down our structure. At a pin connection, we only get 2 forces being transmitted, horizontal and vertical, so we applied them equal and opposite at each joint. And at this point, we were solving 3 separate free body diagrams. And as we identified the different values, we would back substitute in. And we've solved for all our problems. Thank you.